Good afternoon, everyone. Welcome to the Physics Colloquium. This week, we are grateful to have Professor Lian Zhao visiting us from University of Michigan today. Lian got her undergraduate degree from Caltech, PhD from Columbia University. Afterwards, she joined Caltech one more time for a postdoc. Of many prestigious awards, including NSF Career, Air Force Young Investigator Award, and Sloan Fellowship. She's an expert on experimental condensed matter physics, in particular applications of optical methods in quantum materials. And today she's going to tell us about seeing multipolar orders in non-collinear optics.
Okay. Thank you so much, Honor. And thank everyone for being here. And it's been a very great day today to talk with many people and also see the wonderful facilities here on site. So I hope in this talk, I can also contribute something interesting to you, which is our experimental result of using nonlinear optics to see multiple orders. So let's start by saying quite some of us condensed matter people are looking into materials. And when we choose materials, we want to choose those materials with interactions. And even more, we hope the interactions can bring us something. Okay. And is that better? Better? Okay. Okay, yeah, we hope the interactions can bring us something that is very interesting. So then when we look at the interactions, we sort of roughly categorize them into two families. One family is that we hope interactions to be very complex, and we leverage the complexity of interactions to find new things. Another family is that we reduce interactions into lower dimensions and hope this kind of dimension confined interactions could bring us something interesting. Those are two sort of main families of condensed matter people trying to look for materials nowadays, not including everyone, but including a majority of people. So then let's by saying that the complexity part, so we know that we look into materials. Materials are made by atoms. So those atoms form lattice of the material. So that's 1 degree of freedom. But then what's more interesting is that we care about the electrons inside those materials. So for electrons, we have charge degree of freedom, orbital degree of freedom, and spin degree of freedom. So then it is often the interplay among these 4 degrees of freedom of billions and millions of particles inside your material that are going to give us something very interesting. So we take an example to see what are the interactions that people especially look into. So one example is the so-called electronic correlation, which was defined by the Coulomb repulsion between the charge degree of freedom. So Coulomb repulsion is always there for any materials with electrons. But here, there is one criteria. We want to compare this correlation, this repulsion energy scale with the kinetic energy of electrons. When this repulsion is stronger than the kinetic energy, then it enters into the interesting regime, which is a correlated regime. So which makes the collective behavior being different from individual electrons' behavior. Okay, that's a strongly correlated physics. Another example of interaction we can take a look at is the so-called spin-orbit coupling. That's a relativistic effect at the atomic scale. So that is to say that when your electron orbits around your core, so this orbiting behavior of charge is going to create a pseudo-magnetic field. And the pseudo-magnetic field is going to act on your spin degree of freedom. So field act on spin, and then it will give you an energy scale. If that energy scale is big enough, you can actually flip the orbital orders inside the material. So then this kind of flipping of orbital orders has a terminology of a band inversion in material science. So then that will give us some topological aspect about the electronic wave functions in the material. So then you can see that the two types of interaction in the complexity family are going to lead to either strongly correlated physics or topological physics, which are two main threads over the past few decades in the 3-dimensional materials. In contrast, in the second family, where we care about reduction, it's really started by people's ability of isolate monolayer graphene out of the bulk counterpart. So now you have a nearly freestanding atomically thin material. So by doing so, we get a few benefits. Once it's very thin and it's just one layer, your band structure got changed, meaning that your electrons' energy versus momentum dispersion relationship got changed from the bulk counterpart. Graphene is a fantastic example in this sense, because bulk is a massive electron, while monolayer is a massless electron, okay? But in addition to these earlier findings, later on, people also feel that, oh, because I don't have top layer and bottom layer, I don't have other electrons to screening interactions within my layers. So then this reduction of screening is also very important. And in addition, people also, especially theorists, also know that whenever we are dealing with things in the lower dimension, we typically have way stronger instability and way stronger fluctuations. Sometimes we consider those as bad things, but often sometimes we also consider those as good things. So then 2D offers us a new playground of things that we cannot access in 3D. So this is the reduction of interaction actually leads to the so-called 2D physics. So we think interactions are very important. So then we often in our measurement, we do not measure interaction directly. We actually measure the manifestation or the consequence of interactions. So one type of manifestation of interaction is actually the formation of symmetry breaking phases. So your lattice has particular symmetry, but because of interactions among electrons or electron and lattice or others, your electronic state or magnetic state actually have a different symmetry as compared to your lattice. So then that is a so-called symmetry breaking that arising due to the interactions. So we have many examples in the literature. So for example, we have the so-called charge density wave, where you break the lattice translational symmetry, meaning that the charge part has a longer period than the lattice part. So this breaks translational symmetry. And there's also this so-called nematic phase, where you start with a square lattice, and nematic phase choose one of the two orthogonal direction. That breaks the rotational symmetry of the square lattice. And we have charge order in cuprates that breaks both rotational symmetry and also translational symmetry. And ferromagnetism, which breaks the so-called time reversal symmetry. If you do a time reversal operation, the magnetic moment flips. And then ferroelectricity that breaks inversion symmetry. So these are the familiar sort of like symmetry breaking phases that we know how to measure them. And we know what kind of symmetry they exactly break. And my group is trying to sort of push in this direction of looking for symmetry breaking phases in both 2D materials and 2D and 3D materials, with a particular emphasis of saying that, can we see some particular symmetry breaking phases that are not so easy to see before? And the example is in this talk's topic, that is so-called multipolar order. So let me start by saying, what is the multipolar order? As a like sort of the first part of the talk, I'm going to say that this kind of order is actually very, very important in many materials we're dealing with nowadays. But however, because they are so hard to measure, they are often hidden. So after that, I hope to introduce you a technique that has been there for a long, long time, which is second homogeneization. That is a frequency doubling process. Once you shine a red light onto your material, you get a blue light coming out. So this is a process that materials allow you to happen. But the conventional wisdom is that this process only happens when my material breaks the so-called inversion symmetry. And in my introduction to this part, I hope to convince you that we can push the sensitivity of this SHG to be beyond this conventional wisdom. At this day, we can actually measure SHG out of materials with inversion symmetry. And then utilize this, we can see many things that we were not able to see before, okay? And then we will give two examples that two very interesting state of the matter that has inversion symmetry, but have very complicated electric dipole texture or magnetic dipole texture. The first example is the so-called ferrotational order, which has looping electric dipole within atomic unit cell size. The second example is about a magnet where you have a triangular Kagome lattice. So then we will have spin that are all in or out in the plane that are non-collinear. Okay, so yeah, let's start by the first part. So the multipolar moment is a concept that we perhaps see in classical E&M that is introduced to describe how the electronic charge or the magnetic dipole moment arrange in the real space. So for example, if I only have a charge, then it's a monopole. So for a monopole, then I only need a number to describe it. But if I have a dipolar moment, either electric dipole or magnetic dipole, it will be a vector. For a vector, we need a 3 by 1 quantity to describe it. But we can go one step further. If we arrange two dipoles together with opposite direction, then we will have this so-called quadrupole. To describe quadrupole, we will need a 3 by 3 tensor. And then if we stack two quadrupole together, we get octupole. Yeah, so an octupole, we need a 3 by 3 by 3 tensor to describe it. You can see that the more complex of the arrangement, the more higher rank of tensor we need to describe it. So this actually brings us some difficulties because our existing experimental techniques are mostly vectors. So then to couple into something that is tensor, it will be challenging, okay? And let's see this artificial example here. If it's challenging, what can we do, right? Okay, so this is an imaginary, like sort of a square lattice. For a square lattice, we know it will have fourfold rotational symmetry. I rotate 90 degrees, things do not change. So then on this square lattice, let me put the so-called electric quadrupole on it. And I put it in the very same way in every square unit. So then I will form this so-called ferroic electric quadrupolar order. And we look at it again. For this kind of particular order, if you rotate by 90 degrees, it does not repeat back to itself. So then by looking at this, we will notice that when my multipolar order shows up, it will break some symmetry. In this particular example here, it breaks the so-called rotational symmetry. So if I have a technique that is super sensitive to this kind of point symmetry breaking, then maybe I will have a chance to see this kind of state's presence. Okay. Yeah. Okay. So that was an imaginary picture that I draw a square lattice with ferroelectric, ferroic electric quadrupole. Then if we look into the literature, we will actually find there are many materials or material families that potentially host the so-called multipolar order. So one very well-known example is actually the first example that people call for hidden order. That is the materials involve F electron elements. In those materials, they see something thermodynamically to show an anomaly. But when they try to ask, what is the thing that gives this anomaly? Existing techniques were not able to give an answer to that. So then they named it to be a hidden order there. They know something orders, but they don't know what orders, okay? And evolving until today with building knowledges, people start to get the point that this so-called hidden order perhaps is associated with multipolar order, okay? And then there's another family that is called 5D transition metal oxides. Those are the materials, oxides materials, with the metal elements coming from the 5D row, okay? So the unique part of this family is that your spin orbit coupling and the electronic correlation are on the same length scale. So then they can compete or cooperate. It's case by case. But the consequence is that it may lead to multipolar orders. Theoretical prediction have been predicted there, and some experimental verification has happened in this particular family. And then we also have this new family of magnets that are happening on this so-called Kagome lattice that two opposite triangles merge together. So then you can see the spin has more complex texture as our familiar ferromagnets or anti-ferromagnets. So then to describe this unique spin texture, people know that we need multipolar order to say it. And more so, we have multiferrics where you can engineer the texture of dipole moments in many interesting ways. Since you can create these complex textures, then you call for multipolar moment. And examples beyond this. So then the list goes to very long. But then it comes up to the question, since this kind of thing is so commonly happen in those material systems, and those material systems are actually a very interesting material systems to many condensed matter people. So then how do we see it? So then people actually made tremendous efforts over the years. So I'm going to go through a historical timeline kind of effort here. So the very first kind of effort is that people use indirect techniques to know their presence, but do not know their nature. So those kind of indirect probes include specific heat, magnetic stability, or resistivity measurements as a function of temperature. What they will see is that something bumps at some temperature. So this is good signature of something must happen at that temperature, but I don't know what happens there. Okay, so that's the first type. After that, the X-ray diffraction, neutron diffraction, or NMR, they developed. So they have very good sensitivity to the local arrangement of charge or magnetic dipole moments. It's really their sensitivity to the local environment made them being able to say, okay, here, I'm not having a uniform distribution. I'm actually having some texture in this very local length scale. So that is a second type of technique. We call it a direct probe family, leverages the sensitivity to the local environment. Okay, but more recently, there is another direct technique. That is to say, okay, I'm not having the sensitivity to the locality, but I'm still sensitive to this kind of phase by the fact that now I can actually couple into the so-called tensor order parameter. I create a so-called tensor field, then using tensor field to couple into the tensor order parameter. To induce the so-called tensor field, typically you have to go to the higher order processes because our typical fields are vector fields. Okay, so it is this newer technique that inspired our work of trying to use nonlinear optics to study multipolar order, because naturally for us, optics has developed in a way that driving nonlinear response is no longer challenging anymore because we have very short pulses now. If we have very short pulses, then we have very strong electric field. Then nonlinearity can happen if I illuminate it onto the material. Okay, so that's why, yeah. So then a few very brief words about nonlinear optics. So we use the electric dipole transition as example and illustrate the harmonic generation process. So if I illuminate light at omega frequency and get light at the same omega, then this is our familiar linear optics. When we do optical microscopy, we are doing this linear optics process. But in addition to that, if my field is very strong, this term come out, I will have two copies of incoming light combined together to form a outgoing light that is having a frequency of twice of the incoming. That is a so-called second harmonic generation. 2 omega plus omega equals to 2 omega. And I require two fields to come in together, generate one field out. That's a second order. And on top of that, you can imagine we have third order, fourth order, so on and so forth. So then when we look at them, the difference between different orders is really this coefficient that is bridging the incoming field and the outgoing field. The higher order of the process, the higher rank tensor it is in front of this fields. Okay, and it has good benefits because I have incoming field, I have outgoing field. This tensor really represent the materials information that is bridging the incoming and outgoing fields. So then one property that is prescribed by the Newman's principle is that my materials tensor has to obey all the symmetries of my material since it's describing it. If my material has threefold rotational symmetry, my tensor should obey that. So whatever imposed from the material happens in this mathematical tensor. So then you can use the constraint from the material to define the tensor's form. So then you can see if I have a high rank tensor, then I have more elements that are there for me to discern many different symmetries. So going to higher rank processes give us this benefit of seeing the symmetries with more sensitivity. Okay, that's one benefit. The second benefit is, as we sort of repeating over the past few minutes, that is, if I have multiple copies of electric field to participate this process, I can use multiple copies of the field, which are vectors, but their combination are tensors. So then effectively through this process, I'm constructing a tensor field and then using a tensor field to probe a tensor order. That makes more sense and makes things easier. Okay, so that's a second benefit. The third benefit is to say that since we are using this very short pulse, then we can actually measure dynamics, especially quick dynamics. The integration with dynamic measurement is natural by this technique. Okay, so then we go to our technique itself. Okay, so our technique, as we said, it's a long been there technique that is a second Harmonic generation. So I have frequency omega coming. Most of the light coming out is still this linear process, frequency omega. But there's a small fraction that is at frequency of 2 omega and small fraction of 3 omega, so on and so forth. We only care about up to 2 omega here. And for us to pick out the 2 omega, we just use our color filters, optical color filters to suppress that omega. So the weaker of my 2 omega, the better suppression I have to do for the first omega. Yeah. Okay. For the linear process, it's always the so-called electric dipole transition. So to make the photon excite electron from one state to another state, the process is mediated by electric dipole transition. That's for linear optics. It's always this. For nonlinear optics, we have to be careful because we can have electric dipole process, electric quadrupole process, and also magnetic dipole process, and so on and so forth. The reason for us to do so is because the conventional wisdom tells us that if we focus on the electric dipole process for SHG, it is going to vanish if my material has inversion symmetry. That's why people often tell us that SHG is a great technique to detect inversion symmetry breaking, because the leading order is going to be not there if the inversion is there, and will show up if inversion is gone. Okay, but there's a caveat. So if we can say, okay, when the leading order electric dipole is gone, what about the higher order processes? We don't have to consider higher order processes in linear optics because leading order is always there. But in SHG, leading order can be gone. So the higher order processes, for example, the so-called electric quadrupole process, it's going to be always there, whether or not you have inversion symmetry. So then with this knowledge, it's actually more correct to say SHG is there for any material you measure. It does not have to break inversion symmetry to have SHG. Okay. Okay. In addition to the inversion symmetry, if we design our experiment in this so-called rotation anisotropic way, meaning that I will shine light omega here and get light 2 omega out, and these two beams form a scattering plane, then I can choose light polarization to be either normal to this plane, I call it S, or parallel to this plane, I call P. So then I have S and P for both incoming and outgoing. So I will have 4 polarization channels. So then I will choose 1 or 4, all 4 of the channels. I can do this measurement of recording SHG intensity as a function of angle between the crystal axis and the scattering plane. So in a real experiment, I essentially just rotate a beam around the sample and keep on recording my SHG signal. Okay. And then if I look at this data set, you can directly visualize whether my data has rotational symmetry or whether my data has a mirror there, or whether my data has any other operations there. Okay. So this kind of measurement will directly give you the visualization of other symmetries, for example, rotation, mirror, and others. So then from the data, you directly have this kind of symmetry being visualized. We go one more step to say, okay, given this kind of constraint, what kind of point group it will be for the given state I'm measuring. So that's a mathematical deduction process that helps us to pin down a particular state's symmetry group. Okay, that's our procedure of doing experiment. So in a real experiment, it's really just we rotate this light scattering plane and we plot the data in the polar plots that help us to visualize the symmetries. And this test sample is gallium arsenide. For this gallium arsenide, it has a 4-fold rotational symmetry and mirrors. So you can see from the data, it has 4-fold rotational symmetry and mirrors. So you see that directly from the data. And gallium arsenide has broken inversion symmetry. So then the signal is big. Yeah. So then, SH has been there for a long time. Many people used it to look at structures of non-central symmetrical materials or surfaces of materials, because surface naturally breaks inversion. So then when I started my postdoc in Professor David Shea's group at Caltech, we sort of were wondering whether or not we can use nonlinear optics to study not structure, but also electronic phases. So at that time, we were saying there are many theoretical predictions of electronic phases or magnetic phases that so subtly break inversion symmetry. They break inversion symmetry, but it's a subtle process. Because of its subtle process, you don't see it usually if you use a not so sensitive SH technique. So then we pushed the sensitivity of the SH technique in his group, and then used it to study cuprates and iridates. There we see a inversion symmetry breaking phase that coexist or share the boundary with a pseudo gap boundary in those compounds. But this is really still leveraging the so-called conventional wisdom. We leverage the fact that SH sees inversion symmetry breaking. We just make it more sensitive to inversion symmetry breaking and made this progress. So then when I started my own group at Michigan, we want to go one step further. We said that we have been so sensitive. This technique have been so sensitive. Why do we have to look into non-central symmetric phase? Why don't we try to look at central symmetric phases with inversion symmetry? So that is the first topic I'm going to include. The first example is this kind of head-to-tail loop arrangement of electrodipole moment. So this is sort of challenge the conventional wisdom now by saying that, can we see this state? It's a state which has inversion symmetry. So after the success of this one, then we became a little bit more ambitious to say, for light, especially optical light, couple into electrodipole is often easier than couple into magnetic dipole. So if we can see a electrodipole texture successfully, we also ask ourselves, can we see magnetic dipole texture through this technique too? Even though it can be harder, but we want to have a try. So that will be the second example I'm going to include after here. Okay. Okay. Yeah. And if you have any questions, please feel free to just stop me at any moment. Yeah. Okay. The first example, the sphere rotational order. So as we said, it's always this kind of head-to-tail loop arrangement of electrodipole. And whenever we see a order, we always use two particular symmetries to classify them. The two particular symmetry is time reversal symmetry and spatial inversion symmetry. The reason is really because we have magnetic field that breaks time reversal, and we have electric field that breaks spatial inversion. That are the most familiar fields that we have. So then that's we do this classification here. So for this so-called fair rotational order, it has both time reversal symmetry and spatial inversion symmetry. So it's not going to change if we do this two operation. So then that means a single electric field or single magnetic field cannot couple into this guy. Yeah, this is sort of in contrast to our magnetic dipole moment, which breaks time reversal, even though preserves spatial inversion. So then our magnetic field has the same property. So magnetic field measures magnetic dipole. And electric field is similar argument. It breaks spatial inversion, but preserves time reversal, same as our electric field. So electric field controls electric dipole moment. And another thing is here, the so-called toroidal moment, which is a head-to-tail loop arrangement of magnetic dipole. For this texture, it breaks both spatial inversion and time reversal symmetry. So for both of them breaking, we actually can use two orthogonal aligned electric field and magnetic field to couple into this thing, because combination of electric field and magnetic field will break both symmetries. But the thing is that for a thing that contains both symmetries, I cannot use electric field or magnetic field single copies to make it. So that's why this state has been hidden for a long time, even though theoretically, it was known that many oxides material should have this state existing. And some people even say that many of the interesting phases need this state to be as a prerequisite for later on a lower temperature state to happen. But no characterization for this state, just because it's hidden to our conventional techniques. Okay. So then when we started our group, we thought, okay, let's choose a compound that may host this interesting ferrorotational state and use our technique to take a look. The compound we choose is a type 2 multiferric compound, rubidium ion molybdenum oxide. That's its crystal structure. So we pay a lot of attention to its symmetry. So the symmetry is that at the high temperature, it has a so-called bar 3M, which means we have threefold rotational symmetry and 3 mirrors that are 120-degree rotated from one another, and also a spatial inversion symmetry. So those are the generators for the state. Okay, and then there's a critical temperature below which the octahedral cage that is green here either rotate clockwise uniformly or counterclockwise uniformly. So once this happens, we know the symmetry must reduce. However, people didn't know which symmetry it reduces down to. People tried diffraction techniques, but they gave us 3 possibilities with equal suspicion among them. Okay, so then we looked into this state. What we say is that for this particular state, if we look carefully, once this octahedral rotation happens, my ion initially was aligned in this mirror plane, gets deviated away between positive ions and negative ions. So then effectively, I will have a tangential moment that happens at the original mirror direction. So this electrodipole moment will actually loop like this around the cage if we rotate counterclockwise, and loop in the opposite direction if we rotate clockwise. So this is mimic the ferrorotational state that we were looking for. Okay, so then we do our measurement. Our measurement was this so-called RSHG, and we do it in all 4 polarization channels, P in, S out, and so on and so forth, 4 channels. So we can see by the combination of these 4 channels, we clearly see the required threefold rotational symmetry. And the dashed line are the mirrors. Clearly we see for all of them, we have 3 mirrors. And because the structure information is so known, there's an inversion symmetry. So then we know that this signal will just come out from the so-called electroquadrupole process, because electrodipole process is suppressed since the inversion is there. But yet we can still get this good data quality. And we can simulate the electroquadrupole response under this symmetry point group and use the functional form to fit our data. The fits are the orange lines. It fits pretty well. And by doing so, we can also rule out other possibilities. For example, you may ask, the surface Braggs inversion, how do you know your data is not coming from surface electrodipole SHG? The reason is that it will show a different flower pattern after we simulate out. And our data is distinctly different from that. And then it rule out electrofield-induced second homogeneization and bulk magnetic dipole SHG. So leave us confidently with this electroquadrupole SHG. So then from the simulation, we see that the coefficients are actually pretty complex. You have 5 coefficients, and these 5 coefficients are actually linear combinations of 10 parameters. That's too complicated for us to see physics. So then we make the experiment simple. Instead of doing oblique, let's do normal. Once we do normal, you can see that we can pick out one element in particular to look at. So looking at one element makes us our experiment in a collinear fashion. Okay. So then these are the so-called parallel and cross channels. Okay. So then now we have a way to really measure this central symmetrical material. We want to see what happens if we cool down to low temperature across that critical temperature where the phase transition happens. So that is a result. It was initially this even for loop thing that is very well aligned with the dashed line. Dashed line aligns to the values. As we cool down, so below the critical temperature, a background all of a sudden pop up. In addition to that, you can see the flower patterns start to rotate away from the dashed line, which are the original mirror direction. So then if I still do a flip about the dashed line, my pattern cannot recover anymore. So this rotation suggests us that we will have to break mirror symmetry to understand the data. Okay. So this rotation away from dashed line is a strong indication that the original mirror is no longer the symmetry of my data. If it's not a symmetry of my data, it must not be a symmetry existing in the material. Okay, that's the argument here. And then we look into the three candidates that diffraction techniques gave us. So for these three candidates, 3M contains a mirror. If you have a mirror, it's to say that my pattern has to lock to the mirror direction since that's a spatial direction. So our data does not lock, so we rule it out. Another example is called 3-2. 2 is meaning that instead of having a vertical mirror, I have an in-plane two-fold rotational axis and 3 of them. So if I have this spatial direction, then the pattern has to lock to any spatial direction. And the fact is that my pattern can rotate around. So then that also rules out this 3-2. And bar 3 is a point group that has inversion symmetry and threefold, but do not have any spatial direction in the plane that allows the flower pattern to rotate around. So this is the optimal candidate to interpret our data. But simultaneously, from this simulation, we will see that the valley goes to 0 perfectly, while my data actually has a huge background. So why is that? The reason is because we said there are 2 equal possibilities of the state once you go across this temperature. You rotate this way or you rotate this way, opposite ways. So then the reason for us to see the background is really because the signal was so low. So then we had to blow up our beam to survey more materials to accumulate my signal. But the beam was so big that I cover both domain states. So then imagine you have one rotate this way, the other rotate this way, you add them together, then the valley cannot happen because the valley happen at different angle for different domains. Yeah. So then the data was fitted by a weighted add up of the 2 cases. So for this particular temperatures data, it's 40% of counterclockwise and 60% of clockwise to add up to give this data. So then we don't feel very exciting since our beam is big to cover both domains. If we want to see individual domains information, we are necessary to shrink down the beam. And then better, we can raster the beam across the sample and then construct a domain map. But the thing is that using this big beam, I'm only getting like 15 femtowatt. If I shrink the beam size by 100 times, my signal level is going to go down by 100 times of a weak 15 femtowatt. So then we need technique to sort of make this detection more sensitive, essentially. So we just made this effort. So then after doing so, you can now see the domain map of the fair rotational order. The blue and the yellow represents the 2 opposite rotating cases. And then this 2 map is just highlight one versus highlight the other one. Okay. So then by improving the sensitivity, we finally can see the domain distribution. And then once we can see the domain distribution, one experiment we now can do is that we can do the dynamics. So if we have both domains when we do dynamics, it's a bit confusing. So then if we can zoom in to one domain to do the dynamics, things could be cleaner. So then to do the dynamics, we will still use the very same detection procedure. But on top of that, we will introduce a so-called pump laser. So basically, we will give a blast of laser excitation onto the material. And then following that, I do the flower pattern measurement. And then I can tune the time difference between the excitation and my measurement. Okay, and you can see that once we do that, you will see this kind of beautiful oscillations pump up in the time result measurement. And horizontal axis is in time scale of picoseconds. But different from the time resolved linear optics, in linear optics, what we can say is that a change of intensity is just a change of intensity. But in nonlinear optics, since we have this kind of anisotropic flower pattern, a change of intensity in one angle is actually convoluted by 2 things. One is this flower pattern become big and small. The other is this flower pattern shake left and right. Even the size do not change. Once you shake at a single angle, you will see the change in intensity. So then that's the 2 cases. So in order to disentangle these 2 cases, we really have to do a hard measurement. That is, park at every delay to do a flower pattern. This is a force color map of park at every delay to do the flower pattern. So then a vertical cut at a given time will be one flower pattern. So for every flower pattern, we will get the magnitude of the flower pattern and also this orientation of the flower pattern. So then what we will get is these two data sets here. And they are independent of each other now. And the interesting thing is that you can see the beating profile for these two traces are actually different, which is telling us that we at least have 3 frequencies happening in these 2 channels. This is something new because when people looked into this compound before, they used time-resolved linear optics, they only see 1 frequency. And we can see 3 frequencies. And the reason is because we really coupled into this order parameter by symmetry. Yeah. So then how do we say we coupled into the order parameter by symmetry? We try to understand it. So we said we are using the so-called electric quadruple process to do this measurement. For electric quadruple process, we have 4 vectors participating in the process. 2 copies of incoming field, 1 copy of outgoing field, and 1 copy of the wave vector, because quadruple radiation depends on the gradient of the field, which is essentially the optical wave vector. So then it is these 4 copies combined together to form such a form. Such a form has exactly the right symmetry as the so-called ferrotation order. And any fewer vectors cannot construct together to give the right symmetry. So that's why linear optics cannot see it. Yeah. So that is the first part and first example. So we can see the second example. We move to this case with spin has an interesting texture.
Actually, I have a question on the yes.
Yeah.
So, you've shown us here that linear optics can't access this. What are these?
If they do linear optics as if there's no phase transition. So basically, I record the intensity of reflectivity. I will just see a flat line as a function of temperature. Yeah. The reason is because for linear optics, it cannot tell the difference of the so-called bar 3 versus bar 3M. Linear optics, the tensor of these 2 are exactly the same. Yeah. Okay. Yeah. We move to the second example. Second example is a wire semi-metal cobalt tin sulfide. So wire semi-metal was actually a popular topic over the past few years because now you can realize this kind of linear dispersion band structure with pairs of them. So one pair has one of the 2 in a pair has 1 chirality, the other has the other chirality. And then in order for this kind of particular wire semi-metal phase to happen, you have particular requirement of symmetries. So you either have to break spatial inversion symmetry, or you have to break time reversal symmetry to really lift the degeneracy of the cone. Okay, so for the case of break spatial inversion symmetry, there are many, many examples. Like they can be either polar or chiral. Both of them break spatial inversion symmetry. And what's more exciting to optics people of these compounds is that, so there's a whole list of theory and experiments done in this non-central symmetrical wire semimetals. And they include SHG, photocurrent, and second harmonic Hall effect measurement, so on and so forth. The reason for them to look into this is because now the inversion symmetry is breaking. All the second order nonlinear processes that are mediated by electric dipole are going to happen. And more importantly, if you make their frequency low enough, the strength of them is actually proportional to the barrier phase of this wire semimetal. Essentially meaning that you can use nonlinear optics, not only see the symmetry of the material, but also see the wave function topology of the material. That's the whole driving of this many research in this non-central symmetrical wire semimetals. But if you look at the magnetic wire semimetals, there's nearly no nonlinear optical measurements in them. The reason is because for those materials, often they have inversion symmetry. When they have inversion symmetry, the leading order electric dipole is gone. So then people would just naturally think maybe the nonlinear response would be so weak and not so interesting to look into them. So we try magnetic wire semi-metal, cobalt sulfide, as example to demonstrate. It's still worth of looking at them, and they can actually give us very important information. And the focus of my work is trying to resolve the magnetic structure of it, because we said we have to use the magnetism to break time reversal symmetry so as to realize the wire semi-metal phase. So then it is natural that what type of magnetism it is breaking the time reversal symmetry matters. Yeah, so it's necessary for us to know the magnetism. Okay, cobaltine sulfide, it essentially has the very same symmetry as what we showed before. It's a so-called bar 3M, 3 photorotational symmetry, 3 mirrors, and inversion. So that's good. But what's puzzling in the literature is really what is the magnetic order in this particular compound. Even though people think it's a magnetic wire semi-metal, the magnetic order itself is actually debated. Okay, so there are 2 critical temperatures being raised in the field. One is 175, the other is 125. So what's interesting about this compound's magnetism is that you have to think the outer plane spin moment and the in-plane spin component separately, which is not common for many magnetic materials. Many magnetic materials, I just think the spin one direction, that's enough. Yeah, here, think separately. So then separately thinking below this 175, the outer plane component is going to order ferromagnetically. That everyone agrees. What people don't agree is how the in-plane component works. So there are people saying, right below this one, it's already an anti-ferromagnetic order. Other people say, no, below this one, your in-plane component is dynamically fluctuating. Okay, and then below 125, the outer plane component is still have no doubt ferromagnetism. In plane, someone says, no, your in plane component all got pulled into the outer plane direction. It's just a very simple ferromagnets with outer plane spin. Other people say, no, your fluctuation turns into a frozen but disordered state. They call it spin ice. That's one argument. Another say, no, it turns into an anti-ferromagnetic order. And for anti-ferromagnetic order, the literature provides 2 options for us to look into. Okay, so it's very confusing there. So then we think, like, let's just do SHE to take a look. Our goal was very simple at the beginning, whether or not we can see 125. If we don't see, then the story ends. If we see, we need to do more analysis. Yeah, so that's still a room temperature. Room temperature just verifies that we can do the measurement, at least for room temperature. So then once we see the signal, we just choose one angle and then do a temperature dependent sweep. So then this circle is a second Hauman generation signal. You can see flat and then kick up and then another kick. So for the SAG, I do see 2 critical temperatures, one at 175, one at 120. Okay, in contrast to that, I do linear reflectivity, one at 400 nanometer, one at 800 nanometer. I see nothing, it's flat here. So then this tells us that SAG is seeing something that linear optics cannot see already. Okay, so then we want to get an understanding, what is SAG is seeing here? So then we still do the same measurement. We take flower pattern at high temperature, we take flower pattern at low temperature. That's our sort of procedure. So then here, the gray pattern is a high temperature, the blue pattern is low temperature. So what we see from the first line is really like the blue pattern at low temperature become bigger. And then if we look very carefully in the orientation, which we don't see in the polar plot, but we can see in this Cartesian plot, the blue pattern and the gray pattern are shifted a little bit in phase. The shift in the polar plot is essentially a rotation of the flower pattern. So then from high temperature to low temperature, 2 things happened. The intensity grew much bigger than before, but the orientation changed to teeny tiny. Okay. And then we want to know, what does magnitude mean and what does orientation mean? So then we survey across the sample at different points. So what we see is at low temperature, what we see is that at every location, the intensity is consistently increased, while the orientation of the flower pattern can be either clockwise or counterclockwise. So this tells us that the intensity and the orientation are probing different things of the state, because the intensity cannot tell the time reversal related states, while the angle orientation can tell. Okay, so then our analysis is to attribute one is proportional to the order squared, the other is proportional to the order itself. Okay, so then we can still do this kind of temperature dependent flower pattern to separate out the temperature dependence of the intensity and orientation. The main result is really that for the intensity, we have three contributions, one from the bare structure, one from the first phase transition, one from the second phase transition. What's impressive here is that the exponent of those two phase transitions, the first one and the second one have different exponents, and they nicely meet with some theoretical models. The first one met with a 3D Eisen type of exponent, while the second one met with 3D XY type of exponent. So for the first one, it makes sense because I'm dealing with the outer plane ferromagnets. It's an Eisen type thing. So that's this picture. But the second one, it's XY type, meaning that the spin better to be aligned in the plane. So then our data is most consistent with this kind of all in, all out spin textures in the Kagome lattice. So then to form a collective picture, what happens for this magnet is that high temperature paramagnet below 175, the outer plane component forms the ferromagnetic order. The in-plane component was fluctuating at that moment. And then below 125, the outer plane component remains. But then the in-plane component from a dynamically fluctuating situation going into an all-in, all-out state. So then at low temperature, your spin is doing this, sort of most of it is out plane, but you have a cant into the in-plane. And when you plot the in-plane one, it's all in, all out. Okay. So then with that, I'm going to finish the talk and conclude to say nonlinear optics is useful in terms of seeing multipolar order. And we showed two examples of that. And thank you so much for your time.